Mehmet Belviranlı, when did you meet Mehmet in ISC?
Probably OSC or ISC back in 2019 or 18.
ISC when you was in Istanbul, right? No.
It was somewhere in Germany, I guess.
ICS, sorry, ICS. I think we met at ICS when we were presenting a paper.
Yeah, exactly. Yeah. It was way back in 2016.
Yes, yeah. And then he was a postdoctoral researcher at Oak Ridge National Lab. And then he joined Colorado School of Mines as a faculty. And we collaborated for a year on a project and published a paper together. And now we start working more on accelerators, deep learning accelerators or AI accelerators. Okay.
Thanks for the introduction. Yeah, we had quite a bit of long history, which is nice. Thanks for hosting me here. We have a very nice campus, and I would love to see more about it. We'll just test this one.
By the way, if you would like to chat with Mehmet after the talk, he's around today. I'll just tell him for lunch around 1 to 2, and because I have a lecture after this talk, please talk to him. He would be.
Yep, and then I'm going to make my talk interactive, so please feel free to interrupt me anytime you want. So I will just land. If I have too many questions, I will just I can cut over this from the second half of my talk so that I can answer your questions. Yeah, I'm Mehmet Belviranlı. So this is a QR code to my webpage. A little bit about myself before I start. This one works. Yeah, click on that, right? Yep. So I got my BS and MS in Bilkent, then my PhD at UC Riverside. I was a postdoc at Oak Ridge, then staff scientist, then I started as an assistant professor at Colorado School of Mines in August 2019. And that's pretty much about me. So I want to start my talk by deciphering the title, right? If I put a title, it needs to be explained. So the title, I can break it down into 3 components. Is this cutting off the screen? No, right? It's not cutting. No,
I think if you do you mean the Zoom?
No, the top bar is not cutting off the screen, right? Yeah, I don't think it is.
No.
Yeah, okay, nice. So I'm going to start with this middle part, what we're doing in this talk. That's the first part of deciphering. So we are doing neural network inference. Where are we doing this on diverse heterogeneous systems? I'm going to explain it, what it is, what SoC is in detail. And this is what actually we propose. What is the novelty of our talk? We are proposing and we are arguing that multi-accelerated execution on these architectures is good or is beneficial. I'm going to start with the latest bit here. So I'm going to talk about what is diverse heterogeneous SoCs. But before I do that, I need to talk about something else, which is domain-specific accelerator. So when we put them together, it's going to be an SoC. So the need for domain-specific accelerators actually have been there for a while. So CPUs, the most common type of processing units that we employ pretty much everywhere, is a very general purpose processor. What does it mean? You can do pretty much everything, every type of computation, maybe except the quantum computation, right? So you can do pretty much everything. And it is usually employed and programmed using common ISAs, x68, x64, 86, and ARM. And CPU is the most common example. But we're not going to be talking about CPUs today. We're going to be talking about accelerators. And these are usually called domain-specific accelerators. I'm going to be using ESA and accelerator interchangeably in my talk. So these are, again, there's a very wide range of domain-specific accelerators. and as you specialize more, you increase the efficiency. But again, when you specialize, it doesn't do anything else other than the actual function that it is designed for. The most common DSA example is GPUs. Nowadays, I don't know if it's even considered domain specific anymore, because you can do pretty much any computation on GPUs. But back in, at least like before CUDA started, it was GPUs are designed to accelerate matrix operations and merely target the graphics, accelerating graphics. And then over the course of 10, 15 years, it shaped the industry, right? Machine learning and AI, it gave a significant boost. But nowadays, we are not really, maybe for training, we are using GPUs, but for inference, we're going to be using more and more specialized units. These are going to be like one of the accelerators we're going to be targeting. I don't want my panel to be on the display. Maybe I should just my camera. Okay. I'm just going to stop my video there. So one of the specific, targeted and specialized type of accelerator we're going to talk is the DLA, deep learning accelerator. These are not necessarily faster, but they can do the computation very efficiently. And we're going to define what efficient is in the next slide. And again, one other common is if you're using a smartphone with a Snapdragon or Apple processing unit, you will have neural network processing units or hexagon DSPs, which is the most common DSA. And of course, as we go further, we have programmable logic, FPGAs, CGRAs. These are more like application specific, not really domain specific. You synthesize a kernel and you run it. And if we go beyond, we have hardwired circuits like digital analog converters are a very common example for that. The particular property that I want to talk about, which I was mentioning efficiency, is when you look at these accelerators and when we compare it with CPUs, even GPUs, what we see is an increased efficiency. And we define efficiency in this context. It is Bill Daly's paper. So images per watt for a deep learning application, or M cells per watt for a genomics application is the type of efficiency we define here. I mean, these DSAs are not necessarily faster, but they can do the computation at a very fraction of the cost that the CPUs are going to do it. And as you can see, this y-axis is scaling exponentially.
Can you give an example on domain versus application specific?
Machine, for example, deep learning accelerators, right? The DLA that we're going to talk about is able to accelerate convolution, rarely pooling, multiple types of applications. But usually when you use FPGAs, yes, they are capable of synthesizing. You can synthesize multiple kernels into one kernel, one FPGA binary. But usually the primary, the common usage pattern is you synthesize an entire kernel, you employ pipeline or whatever parallelism that you want to employ, and you push it into the GPU. So that is the differentiation I tried to make over there. Yeah, specific. Maybe a better word will be kernel specific. That might be better.
Sorry, what is ASIC? I'm not.
ASIC. Oh, sorry. So it is application specific integrated circuit. Basically, DLAs can be considered as ASICs. So they are targeted, designed to have specific functions only. Like if you think in the broader sense, CPU itself is an ASIC, but it's capable of running an ISA. But the common usage in this heterogeneous computing is when we say ASIC, they usually refer to domain specific.
So for instance, is TPU and ASIC?
I would say so, yeah. Again, the terminology is sort of quite evident over there. The takeaway from this slide is accelerators provide increased performance per watt, and that's sort of the main theme of today's talk. Any questions on this slide? From Zoom? Okay. And there's a trend. When we look back in 2010, Apple's A4 back at the time employed only 4 accelerators. But 2019, this image was taken from Harvard's, I think it was David Brooks' page. They did a reverse engineering on the die of Apple's A12 chip, and they were able to identify at least 42 blocks that are dedicated for specific computations. And you can think of any API call that requires some sort of a computation, major API call in iOS API, they are mapped to one of those accelerators. They're only programmable by Apple's APIs. However, they really do their task efficiently. Examples will be video decoders, encoders, SHA encryptors, maybe camera decoders, and we can list many. And they don't really serve too many purposes other than their design target, but they do that, their design target very efficiently. And again, the takeaway from this slide is there's a trend, increasing trend in accelerator count that we put inside those system on chips. Now let's think about more about let's talk about system on chips, what they are. Nowadays, basically everything is a system on chip because maybe back in the days, early 2000s and even before that, the CPUs were really merely including cores and caches. They didn't have any memory controllers in it. They didn't have really any additional circuits in it. But nowadays, the more circuits you put, the more interconnects you put, it becomes more of a system on chip where it contains more than just the computational cores. So that's where historically the system on chip term came. But in this talk, we're going to be using this SoC term specifically for the chips that are used in mobile autonomous computing. We all have them in our phones, and they usually employ, as we showed in the previous slide, they usually employ dozens of accelerators. And in this case, we're going to be focusing on a more targeted, more beefy accelerator. The figure you saw is the one that we experimented in this talk, which is Xavier AGX SoC. And what we see here is we have a CPU, we have a GPU, but we have multimedia decoders, a deep learning accelerator, we have a vision accelerator, and they are connected to, that's an important bit, they're connected to a shared memory bus. The memory itself is not on the chip, and usually that's the common design pattern, but there might be exceptions. And this is pretty much the same pattern all these very popular SoCs follow. And we're going to be focusing on this specific type of architecture. Any questions so far? All right. So the next part of the title is what we're doing is neural network inference. This is probably a figure that you see hundreds of times. Here we have convolutions, pooling, and then finally we have fully connected units, which gives us the classification. But more importantly, we want to make a distinction between inference and training. Training is more of a problem for HPC and data center research, but inference in this case is we will be focusing on in the context of again mobile autonomous computing. I will be using edge for this domain. So first of all, it doesn't have backpropagation. Inference doesn't deal with big data. It rather runs on incoming data stream in our use cases. It may be video, an image stream, a LiDAR point cloud. But the most important bit is it is often deployed, and in the target use cases we are going to focus on this focus, it is often deployed in scenarios requiring low latency or low energy. And this is the two targets that we will be trying to achieve with the scheduling algorithms we are proposing. And there's another term, it's again another buzzword. I took this nice picture from Polo.ai. They provide these NVMe-based AI accelerators that you can plug in. I'm still waiting. I ordered like a year ago and I'm still waiting to get one. They call it on-device intelligence, object detection, pose estimation, image segmentation, key phrase detection. And these are all pretty much nowadays handled by neural networks. Back in the day, there were a lot of like conjunction of computer vision algorithms, but nowadays there are end-to-end neural networks that are handling most of those stuff. So we talk about SoCs, accelerators, we talk about neural network inference, and let's now focus on how we accelerate neural network inference, right? GPUs have been the primary driver. We all know that, both for training and inference. But nowadays, GPUs are not really enough, especially for mobile systems. And all these actually big players have implemented their own version of neural network processing units. They all name it different things. Again, we're going to be focusing on deep learning accelerator developed by NVIDIA. And this is these are really the pictures of these architectures. I picked them one by one. So all these architectures embed at least one specific unit for neural network processing. And now the actual bit, what we are doing in this talk and why it is important, why you should listen to this talk, right? We are doing multi-accelerator execution, and I'm gonna make my case, but I just wanna, by giving you two scenarios, I'm gonna argue that multi-accelerator execution is important. But before that, I just wanna dive a little bit deeper into the architecture that we're targeting. As I said before, we have CPUs, we have a GPU, CPU cores, GPU, two DLAs, we have decoders and encoders. I think Vision Accelerator is not shown here, but the most important bit here is we have a shared memory controller fabric, and we have a shared memory. So, when we're writing papers, one of the first things we do when we get an idea is to evaluate the feasibility of the idea, whether it's going to work. And the idea that we came up first was, yes, we know GPUs are powerful, but what about this DLA? Let's focus on this and let's try to discover what it can provide for us. And one of the things that we did was stress tests. So we basically find the GPU stress test and run it. And luckily, this architecture provides a very detailed hardware counters to measure the power consumption. And it is very detailed. As you can see, the components are very nicely broken down. Here we see GPU power, and because this DLA is not directly programmable, it's not general purpose, we ran a large convolution with a large filter size, which we believe it is a high computationally intensive workload. And this CD power is the name of the counter that gives us the DLA power consumption. And as you can see, while GPU is using almost 25 watts, DLA was using 5 watts. Of course, it is not as fast, but there is a significant difference in power. Approximately, ME-DLA consumes less than 1/4 of the GPU power, and you're going to see in the experiments we're going to show shortly, it provides half of the performance at the expense of the 1/4 of the power. How much energy does it make? How much energy save? 100%, half of the DLA spends half of the energy that GPU will need for a specific type of computation, and that's quite good actually. It can be a very good candidate.
So can you go back?
Sure.
That's the green is DLA.
So the CD power.
That because
we were using just one of them.
Okay, so the power consumption is just for one of them, or for?
No, one. And so at the time, it's still currently you cannot really you cannot distribute the layers of one neural network on two DLAs concurrently. So we just focused on one of those DLAs.
But normally there are two, or I'm not sure.
In both Orin and Xavier, Orin is the most recent architecture, and in both architectures there are two. And they made it faster in the recent iteration. So these, most of the experiments I'm going to show today are from the older generation, 2 years old, I guess. It's from the Xavier architecture.
So, safe to say that it's 1/8 of the GPU power, isn't it? 12%.
Is it? It's less than 20%. No, more than 20. So it's 25 watts here and 5 watts here. More than 5 watts, less than 20. Did I do the math wrong?
No, sorry. In the DLA, you're counting a GPU, so you're just counting the GPU.
I'm comparing the DLA, one DLA's power consumption to the GPU, and it is.
Yeah, I told the entire chip. That 12% is the entire chip. power consumption for the entire chip.
Yeah, for example, the specific question we were trying to explore here is, if we were to push the processing unit into boundaries, which will mean that we're going to be using it efficiently, right? By stress tests, the GPU maxes out at 25 watts. We have much more detailed power measurements, energy measurements, but this is more like the very first experiments we did to discover like how beefy, how power hungry those accelerators are. And it is just to show that DLA is really very power efficient. And it is doing only a specific type of tasks, but it is doing them at a very fraction of the power cost. That's the takeaway. Is that clear?
Yeah.
Okay.
I will just.
I have more numbers.
Use the math, not. I got what you're saying.
Yeah. I have more numbers.
The GPU power, not the entire chip's power.
Oh yeah. Yeah.
Okay.
All right.
Thanks. So M.Belviranlı stands for
DLA, or M.Belviranlı is sort of the I will say the verbose name, because they just want to put that M brand. But in their documents, they refer to simply DLA. But this architecture is actually open source. Initial iteration is open source. You can download it and flash it on an FPGA.
Okay.
But I don't know the release of sources for the latest versions, but the architecture itself is open source. And there are several papers that investigate these architectures by flashing on FPGA, but we use the real system provided by it.
Can I ask one more question?
Sure.
I'm just curious. So how do you measure the power consumption on specific parts of the architecture?
Yeah, so that's actually a beauty of this architecture. It just comes with the hardware copies. So it's very uncommon for larger systems, but that was one of the things why we prefer to use this system in our experience. There's a command called Tegra stats, and when I do like it dumps everything. So what we did was we did an S-trace on this Tegra stats, and we were able to find which device pointer, device file is corresponding to what type of content. Good. So my talk has two parts. I'm not sure how much of them will be covered, maybe partially part two, but I want to talk about the first part. These two parts are depending on two scenarios. This is more like a motivational slide. I'm going to be actually talking what we do once I talk about these two scenarios that we want to target, and then I'm going to be actually starting the actual content. Let's think about a quadcopter drone. Usually they have some perception logic implemented, right? They detect objects, they track objects, they try to avoid obstacles, they try not to hit walls. And in order to be able to efficiently do that, you need to have a low latency processing capability on those devices. And this is usually the main target of the system. Otherwise, if you have a high latency, your reaction time will be low, and you will not be able to fly at all, right? That's the primary objective of such cyber physical systems. However, there are constraints, and one of the constraints we will be focusing today is battery. So let's think about a case where your drone is running out of battery, but you still need to return to base safely, right? If you keep processing at the same speed you were flying before, you may not be able to make it. And that's a crash, that's bad. But if you reduce the processing speed like to dangerously higher latencies, then you may also crash again. So there is a trade-off. So you want to save energy, just right amount of the battery you left, and so that you can make your base station. And in the meantime, you want to maximize, you want to minimize the latency of your flight processing perception algorithms so that you reduce the risk of crashing some obstacle because you were able to realize that the obstacle was there. It was too late when you realized it, right? So there is a trade-off. So what we're going to do in this first part is basically, we're going to be defining a constraint-based objective optimization problem. And we will be giving, okay, this is your limit, this is your budget, energy budget for processing a single image. And you need to be under this budget, and you need to do that processing unit as fast as possible. So that's going to be what we're telling to the perception algorithms running on the drone. Any questions with this one? I'm going to show one more experimental example. Okay. Again, the second step of our feasibility analysis was, let's see whether we will be able to achieve this trade-off at all, right? So you see a highly abstracted visualization of, I think this is VGG19. And as you can see, CPU does some pre and post-processing, but most of the computations are done on GPU. Almost all of the heavy computations are done on GPU. So this is a case we call standalone execution. So when we run everything on the GPU of the Xavier system, we get 8.5 milliseconds per image with this much of energy consumption, 205 millijoules. And of course, we also have a delay in that system, and we claim it's energy efficient, and let's run it, and let's see, and we ran it, and we saw that, yes, it is quite slow. At this time, it is even slower than 2x, maybe close to 3x, but it saves some power. And there are cases where it saves more power, and it is more faster than this. But just for the sake of this example, I want to focus on these two bits. So let's say you have some energy budget per image, more than 140 millijoules, but you don't have that much available in your battery. So what would you do? Let's say you have 170 millijoules available. You did some math. Of course, these are not really like a precision accurate. You cannot really calculate the energy that much precision, but at least on the longer run, when you take the average, you're going to get a pretty much accurate number. So let's say we have 170 millijoules, but we don't want to really reduce our latency this much. What will be an option? What can we do? Any ideas over Zoom?
Mixing them, GPU and DLA.
Yeah, so we can look at this, quite obvious, right? So what we can do here is we can execute some of the layers on GPU and some of the layers on DLA. And we will be very careful with selecting which layers we will be executing on both accelerators. And we name this type of execution as collaborative execution. It is not a new word, but it's when we say collaborative, we will be referring to this type of execution in this talk. And the interesting bit is, when we do this, the total time per image is going to be 12. It's even closer to the performance that we got with the GPU, but at the expense of a much lower energy cost. And we were able to meet our budget. So the question boils down to is, we can use this collaborative execution to provide a trade-off between energy and performance. But of course, we need to know how much energy we're going to have in the system so that we can set it as a target, as a constraint, and then our objective will be always minimizing the latency. So that will be the first problem we will be discovering in this first part of the talk. Any questions with this? This is more like an introduction of what we're doing, and I'm going to be getting into details.
Does it matter where you put the GPU?
It does. Yeah, it does. Usually, GPU comes up in the first because these are larger layers, but some architectures have the smaller layers in the beginning. So there are also some such models. So our methodology is generic, so it can handle both cases. And these are different trade-off cases. And depending on how much energy you have, you get a different execution time. But because GPU is always faster, the more energy you spend, the better latency. That's quite obvious. This is just a verbose output from your head. The second part is going to be not focusing on the energy, but we have a GPU, right? We have a DLA. We have some processing power on that SoC. And what if we just need power, like very high throughput? Can we use both of them efficiently? And that's actually where heterogeneous computing is coming from and focusing for the last few years. So we are using more than one type of accelerators concurrently to improve our throughput. In order to sort of understand the problem better, let's think about a couple ways to be able to use both GPU and DLA. The very naive way will be, I will not really use this slow DLA. I will just go ahead and use GPU for, let's say your application requires VGG and REST. I think there are some cases where ResNet is used for image segmentation and VGG is used for image recognition. And let's assume we have a workload that requires us to run both of those on the same input, and eventually we will do something with the output of this. So what we do is it's going to be serial anyways because we want to use the GPU fastest. We just execute them back to back. That's the very naive way of executing. But we can be a little bit more smarter. Yes, we have a DLA, we have a GPU. Let's run two things together, two networks together simultaneously on both of those. However, this will cause a problem because of the key property of this architecture, shared memory system. So because, again, this is a mobile architecture, like an efficient architecture, the bandwidth that we have on those systems are not really as generous as the ones we will find in high-performance systems. So the VGG, when we execute VGG on the GPU, yellowish color, what is this color called? It's not yellow, it's not orange.
Salmon.
Salmon, okay, maybe tan salmon, right? So when we execute VGG on GPU, if you notice, it runs a little bit slower. And these are the actual measurements. This is not just a hypothetical drawing. It runs a little bit slower. And of course, DLA execution is already slow, and it is also affected. We don't show how much it is slowing down here. But again, this is the savings that we get is very minor, 6%. But we can do better, and that's the goal of this work. We propose this hexcon. So in this case, we employed both collaborative, the idea from the first part, and also concurrent execution, the new idea in this part. And then we were able to achieve a better result. And yeah, 21% may not sound so much, but keep in mind that this is real system, real networks, real workloads. So we were able to achieve this by switching the execution, by assigning these layers so carefully so that we don't have any idleness because we find a point for each network where we need to transition from one accelerator to another and vice versa. And those points actually result in like same execution time so that we have an equal and balanced workload distribution between those two accelerators. And that's what we model in this paper. So what we take into account is when you want to switch the transition from this layer 27 to 28 from GPU to DLA, we calculate how much this is going to take. We calculate how much this is going to take on the DLA, and we calculate how much they are when they are run concurrently. We factor in the slowdown that will be due to memory computation, and then we find a spot, the perfect spot where this equation is equalized, while also considering which accelerator executes which layer best. So it's again another optimization problem which we're going to be talking about. And the takeaway of this second part is going to be multi-accelerator, collaborative, and concurrent execution can increase system throughput. Again, we don't have any energy goals at this point. So just to increase throughput and energy strengths.
I'm curious about how you do layer search. Is it like trial and error, or is there really. Like
no, not really. We basically, and that's what I'm going to be talking about. We're going to be we do empirical modeling, but we don't really run every network. We do empirical modeling layer by layer, and we rely on this assumption that we use common layers, and all these networks use common layers with common type of inputs and filter sizes, and we profile them beforehand. And what we do is actually set schedule. So I am now one of the proponents in scheduling. We got a project from formal methods in the field. So I'm working with some formal methods people, and now I am leading all my PhD and postdoc I did dynamic scheduling. Now I'm becoming a more proponent of yes, static scheduling also works in some cases. So you can challenge me, and I will do my best to defend. Yes, this works in this case.
So does it work in a simulation environment?
No, this is real.
Real hardware.
Real hardware. I don't have the picture. I think we saw a picture in the beginning, so that this black box with a very huge instant on it.
So these improvements are on the running time, right?
The total cumulative throughput. So your workload is going to require running both of these networks either simultaneously or back to back. Yeah, you can think of like there's a big control flow graph that continues after this. So you need to finish both of those to be able to continue. It may be a loop in the CPUs. cyber physical system. All right, so I can start my first talk. Let's see, I have 20 minutes left.
First
part, no, not first talk, first part. Any questions so far? So we recently published this.
Is there any difference in terms of shared memory in those architectures? Like that part I didn't understand in the previous slide. Like you mentioned two cases, concurrent versus collaborative and concurrent, like in terms of shared memory usage.
These experiments are done on the same Xavier architecture. The architecture is same. The input, and I'm going to show those scenarios hopefully. Depending on the scenario that you're going to have in your system, you may be processing these two networks will be using either different images or same image, because it depends on what you want to do. If you want to show bounding boxes on an object you detected, you will probably like to run them both either back to back or in parallel on the same input. Or if you want to run two instances of the same network on two separate images as a pipeline, and that's something also we discovered. Is that what you're asking?
Yeah, I guess like I was asking, like in terms of like, so in both of them you use shared memories, right? Like,
yeah,
like one of them has benefit over the other one. I would think that the second one will have a benefit over the third one, isn't it? No, because you're relying on shared memory more in the third architecture.
So I think we need to make this distinction. Yeah. So shared data and shared memory. So shared data is not really our concern here, because every type of data we're going to be accessing will be in the shared memory. So it doesn't really matter whether this input is same or different. Maybe that's something that is
the same data at the same time by the same.
Yeah, but it doesn't matter because these two accelerators do not share a last level cache. Maybe that's a detail I missed to say. Because they don't really share the last level cache, it is all memory accesses. So even if it is the same data, it doesn't really make any difference.
So you're saying that when you that they exist like layers from GPU to DLA.
Well, there's a
data transfer happening.
Yes, and that's what this one of our characterization, one of our profile, and that's one of the important bits.
Mention that there's shared memory access. So I thought there's no data transfer required.
No, that's the only way that these two accelerators take over. They don't have a shared cache or anything.
Yeah, but you're saying that you still need to do data transfer?
Yes, you need to.
For what? Because they share the memory.
So basically, when you run
their local memory, you have to transfer to their local memory.
They don't have a local memory. Like GPU has internal caches and DLA has buffers. We are using TensorRT, and that's the only way to program DLAs. TensorRT, when you're executing all layers on one architecture, all layers, when you're switching between layers, there is a type called transient data. It can be either the scratch pads in the GPU or caches. But whenever you do this transition, you need to, this layer at this point is marked as an output layer. An output layer forces a flush operation. And it makes sure that all the data used internally, all the transient data used internally is flushed into shared memory so that DLA can read them. And similarly, DLA has an internal buffer. That's the cost we're modeling. So that's the cost. We're going to be looking at the layer cost. We're going to be looking at the transition cost. And in the second part, we're going to be looking at the memory computational side. Is that?
Yeah.
All right, let's start this first bit. So this is the figure you see. The problem we want to solve is we want to find an optimal schedule that satisfies a given energy budget. So we're going to be finding a trade-off. There are two primary challenges, which we just talk about them. So the first challenge is we cannot really characterize every neural network in the world, but what we can do is we can characterize the common layer types and for every accelerator, target accelerator we have. And there are a couple of things we need to consider. I'm going to talk about them. And of course, the second challenge, which is the biggest obstacle we had when preparing this paper, was the transition cost between layers. So if one layer is outputting a very large amount of data, and if you prefer to switch from GPU to DLA at that point, you're going to be flushing a lot of data, and you won't be really using any internal buffers or caching benefits. And we do this by using a SAT solver. We define a problem, a constraint-based optimization problem. We feed into the solver and it gives us an optimal schedule. And that's something I often brag about. So as long as the problem space is linear, we can find optimal schedules with static schedule, which most of the heuristics are not able to provide. This is a more inline example with the numbers that I put in the very first slide. Like this is for GoogleNet, and when you run everything on GPU, it takes 3 milliseconds. When you run everything on DLA, it's a little bit below 6 seconds, and the energy consumption is almost exactly half of the GPU consumption. That was another experiment that my student ran, and I wanted to put this here. Again, there are different trade-offs. This is just an example. But the reason I'm showing you this slide is something else. So when you look at these different type of layer intervals, the DLA is not always equally slow. It's not always like 0.5% slow. Sometimes it is less slower, sometimes it is more slow. It sounds weird when I say it. So that means the layer characterization, there are some layers, although DLA is always slow, still it may be beneficial because DLA is less slow on those layers. And our characterization already addresses that by looking at each type of layer, running on each type of accelerator with different varying size of inputs. And filter sizes are not shown, but also we vary the filter sizes. Yes, it is quite a bit of search, but it is not really like a very exponentially large search space. Still, the number of layers we can use in neural network inference is quite limited. What we end up with in this first challenge, to solve this first challenge, is for every type of layer and their input sizes, we create these energy and time measurements. We collect them. This is often called empirical modeling in the HPC world. So yes, there are ways to do this analytically, but for the sake of accuracy and getting the right results, and for the feasibility of this problem, empirical modeling just works fine in this case. Any objections on that? So this is your expertise, so please feel free to shoot. So this layer execution characterization depends on layer types, target accelerator type, and the data size. And the more interesting bit is the transition. And again, the transient data that is often held within the accelerator when we are executing each layer needs to be flushed out to the shared main memory. That's the problem. And also, that's just half of the problem. The other half is when the new layer is executing and it needs to read, and if it is a cache-based architecture, it's going to be all costing cold cache misses, cold misses. And how do we identify this? So this transition cost depends on multiple things. For example, like how much data that a specific layer needs to output, right? That's one factor. Of course, operation type is important, but also it's important that because we are working on different type of accelerators, the internal memory hierarchy is also important. But again, we took a shortcut and we do the empirical modeling here as well. And this is how we were able to identify. As you may have noticed, these transition costs are not really that much for these specific examples, but when you consider multiple transitions, this is just an extra cost that comes with it. So you cannot do infinitely many transitions, even if you, not infinite, but like, you cannot do like a lot of transitions. There is a limit to that.
I think there's a question.
Does your model change its data, deal model device method based on the requirements? I results ASAP or need results, but I don't want to spend so much energy. Yes, that's a very nice question, Osman. So what we do is we set, and you're going to see in the next slide, we set a parameter, we pass a parameter to the optimization problem, which is called ETC. So currently it is not really like a, you can think of it like a knob. So I have this much energy budget, give me the best schedule. So we assume that in this work, we assume that we always want to get the best schedule that meets the energy targets. So we don't do like, give me the best energy, I don't care about the performance. So in that case, we will simply run the DLA. So that's how we do that. Does that answer your question, Osman? Hopefully it does. Okay, good. So I'm going to spend next half hour on this, explaining this. Of course, I'm not going to do that. So you don't need to read all these details, but what I want to show, there's a time function. It relies on transition costs. There are multiple things over there, but at the end of the day, we're minimizing time and we're giving constraint, and our constraint threshold is energy consumption target. And one of the criticism that we raise at this point is, how do you know like specific millijoules energy consumption target? It's not automated at this point. I mean, you cannot really give a scale 0 to 1. It's more like you execute, let's say you do like full GPU and full DLA execution, and you determine what you want and you pass us that value. So that's how it works currently. And again, when we're doing any type of performance modeling, the first thing we do in HPC world is to verify whether your modeling is accurate. Although we are doing empirical modeling, which means that we are already running, executing what we want to do, but keep in mind that our model relies on layers, but the actual execution, like end-to-end execution result is coming from the full execution of the neural network. So that's what we compare. So we are comparing the times, these dots are the times that our model, time and energy that our model thinks that given schedule will take. And these are the lines that when we actually run that schedule and measure the total energy and total time, and that's what we get. And of course, we have a nice accuracy because we are doing empirical modeling, but in our case, empirical modeling is just this. And of course, there are some other HPC scenarios where you have like highly irregular computation, much more complicated topology in the system. And so you cannot simply do an empirical modeling in those cases. Right? For the scope of this work, it just works. Any questions? All right, so let's check the time. This is the last slide for the first part, so I think we're doing good. You may ask this question, right? So it's always one transition is going to be enough. In some cases, the optimal execution, which means the fastest execution, is obtained by 2 transitions. Yes, there's an overhead, but again, this is much rarer than when compared to 1 transition. And there is even a case where we start from GPU, we switch to DLA, we go back to GPU, and we go back to the, and that was giving us the optimal solution. There's only 2 cases for that. All right, that was the first part. The second part is the throughput part. Any questions so far regarding the first one? Okay, I'm going to cut down this part a little bit, and I want to talk about the most important bits. Again, this is the figure you see. The difference from I just want to put the contrast when compared to the first part so that you can quickly understand it. What we're doing in addition to the first one is we were doing collaborative, but now we're also doing concurrent execution. That means we are using GPU and DLA simultaneously because we don't care about the energy. Who cares about it? And the second challenge is, in addition to the challenges we handled in the first paper was, now we're going to be handling shared memory contention. And of course, in order to solve this, we have a multi-objective optimization, which I'm going to show recently. But again, we are using static scheduling. So this is a peer work that we did, and this work really helped us a lot understanding this architecture. So this immediate Xavier SoC, the maximum memory bandwidth you can get from this architecture is 130 gigabyte per second. But very unintuitively, when we experiment with it, let's say you run a workload that asks 50 gigabyte per second on CPU and 50 gigabyte per second on GPU. Like if you do the math, it is 100, right? You need to have like enough bandwidth. But it doesn't work that way. Both of them get less than what they want. And there are multiple reasons: memory controller contention, maybe DRAM buffer misses, right? There are many row buffer misses. There are many reasons for that. But what we end up with in this other paper is model this behavior. This is the speed that the processor, let's say you're a GPU, and this is the speed the slowdown you experience. If you're asking really not much, And even if your external bandwidth demand is very high, let's say your GPU and CPU is running something at 100 gigabit per second. If you're not asking that much, to slow down your experience is not really that much. But, and this is the most common case. If you are asking a little bit more and the GPs, the other accelerator is asking also some considerable amount of bandwidth, you end up sharing the bandwidth 50-50, but the amount of slowdown you get is significant. So even though like this is probably, like I didn't do the math at this figure, but if you add those up, for example, at this point it is 50-50 where we have enough bandwidth, but when you're slowing down, your application is slowing down more than 20% at this point. Although the total amount of bandwidth you ask is 50 plus 50, which is 100, still you don't get what you want. So what we did was in this work is incorporate this type of like modeling. Yeah, I wanna probably, let me see. Yeah, I wanna skip this one and I wanna show you these scenarios. So depending on the workloads, there are different type of concurrent executions you can do with these neural networks and multi-accelerators. We targeted 4 scenarios, and each scenario, what will happen in a naive case where you don't consider layer by layer distribution, but you assign those neural networks as a whole, right? So in this case, this is the example that I show. Like in this case, we have 2 DNNs. They are working on the same DNN, same type of DNN, working on 2 separate images. You can think of it like a stream and then the same neural network. Or in this scenario 2, 3, and 4, is it possible that we can minimize that? I think it's Alt H, the bar. Yes. Okay, so we have scenario 2, scenario 3, scenario 4. These are different type of DNNs running together, either on the same data or different data. This is more like a pipeline parallelism, and this is again collaborative execution that uses both GPU and PLA. These were the different scenarios we considered in this paper. The other thing I want to mention in this work, I need to skip. Let me see. I want to show the formulation here, and maybe we can bring it a little bit to the right at that thing. Yeah. So the formulation here, we are again formulating the time, but then we are having the contention. We need to model the contention as an equation here, and the contention. In order to be able to identify contention, we need to rely on contention intervals, and that's the last important bit I'm going to mention in this paper. Again, I need to go back. Sorry for skipping too much. But this is an important bit. So we have a model that we want to use, yes, but when you have multiple accelerators running different things at different times, things get really complicated. For example, it's a hypothetical case where you have 3 DSAs, like your layer is running here, this is a different layer, and you have 2 different layers are executing. So the amount of slowdown that this layer is going to experience is going to be different during this interval and this interval. So you need to be able to model this contention differently so that you have a high accuracy prediction. So what we came up with as a solution to define something called contention intervals. And we define this whenever a layer starts or ends at any time in the execution, entire execution, there is like a new contention interval stops. So the idea is within this interval, the external bandwidth that I show is homogeneous. So the amount of contention that each layer, the part of the period of the layer that's been executed here, it experiences the same amount of contention. So that was the idea. And we embedded again this into our formulation, and we fed this into SAT solver. And these are the objectives that we gave to the SAT solver. Here, the first objective is the average latency. That is either this or that. We cannot achieve both objectives, but if you want to achieve average latency or minimize the average latency, we use this objective. If you want to maximize the total throughput, we use this objective. And of course, we got some results that is up to 16% improvement over the state of the art This is a DAC 2022 paper, and I think this is another state-of-the-art work. That's pretty much it. So, right?
Yes.
Yeah. So because the questions were integrated, so yeah.
I'm curious what kind of DNN architectures you have tried. Have you tried, for instance, transformer types or most CNN types?
Yeah, but I think RNNs also before. But again, RNNs will have a problem how many times it's going to repeat, as long as it is within some material. But here, see.
Thank you.
Thank you very much.
So if you use transformer, you need another accelerator. I'm not sure like DLA will work, or DLA is mostly for CNNs.
The DLA has a pipeline of engines, internal engines. So if I remember correctly, I don't know what type of computation transformer requires, but the engines that it embeds is a convolution engine, there's an activation engine. I think they support 2 or 3 activation functions. There's a pooling engine, and that's pretty much it. It's slightly, so I'm not sure if this.
So when you don't use it, it doesn't consume energy.
Yeah, when you don't assign anything to DLA, it's probably power.
Sorry.
I would imagine. I would imagine it's power.
So GPU is saying like if you don't send anything, it's low.
These are mobile architectures. I mean, we had those results. If I remember correctly, yes, they don't really report any relationship like that. But you never know. I mean, it's the values that reported.
Some, but it's not zero, but it's not same as that. It's not something like I would imagine like 1 or 2% maybe.
So we had another experiment. It's not shown here, and it's not embedding my slides. But again, it was one of the early exploration phases. We gradually activated those stress tests. We gradually activated everything, and then everything added up the total system counters as well. So maybe we can look at those results, and I can answer the question more. But I don't. There might be some passive consumption, but these are more like the states, P states, attributes, right? Depending on whatever information between the operations. But one of the things is because these really do not share last level cache, there is no coherence required. So you don't need to really keep the accelerator on to be able to like issue coherence requests and cache coherence plus, and then they get a start from the architecture. So other than that, I don't know what kind of communication that SoC needs to connect needs to do with the
Thank you.
Did you mention that Doa was my mentee back then?
Yeah, I did. Sorry.
Did you?
One of my students, intern, when you.
Yeah, I was there.
Okay, so he's at Michigan State.
Yeah, Michigan State. Any questions from Zoom? Are there any chat questions?
Is your room better or?
No, we're gonna go to 1 to 7.
Okay.
Yes, let's close the session.
So anyone from Zoom would like to chat with Mehmet?
So I've already shared a spreadsheet where people can reserve slots. I think